We'll now discuss about different types of devices that deal with input-output and mass storage. The input-output units are the devices that allow a computer system to communicate and interact with the outside world, as well as store information. Now, the random access memory that we talked about previously is what we consider volatile memory. Here, this means that the information will disappear when the power is turned off. If you ever wrote a paper and you didn't save it and the power went on, then you went back on and then the paper was gone, it was stored in the RAM, but it wasn't stored anywhere else. So when you lost that power, you lost that paper. I mention this because it may or may not have happened to me before. So the whole point here is that RAM is not reliable in that if we lose power or something goes wrong, we can lose the stuff that is in our RAM. Now, if we want to actually store stuff permanently, we need something a bit more reliable. We need some type of long-term non-volatile memory where the information could be saved even when the machine is shut down. So non-volatile storage is the role of what we call mass storage systems. So we can use one of these, such as disks and tapes, to permanently store our data. That way, if we shut down the machine, we don't lose our documents and our data. Now, there are a ton of different types of input-output devices. Sometimes we call these I/O devices. So like we just say I/O. So if you hear me say I/O devices, I mean input-output devices. But we have a ton of different devices that vary in functionality. Now, there are two particular types or two basic types that we can have. There are those that represent information in what we call human readable form. So this is for human consumption. And these, just a couple examples, these are things that humans can read pretty well. Keyboards are input devices that we interact with the computer, monitors, printers. So those are types of devices where we have a human interacting with the machine. The other basic type is what we call a machine readable form. So we're talking about those devices that store information for machines and they're accessed by a computer system. So things like flash memory, hard drives, CDs, DVDs, and tapes. Now, these devices also come in two distinct forms. So we have what are called direct access storage devices, or DASDs, and then we also have sequential access storage devices, or SASDs, and we're going to talk about both of these forms in more detail. Now, when we talked about random access memory, there were two fundamental characteristics of random access. The first is that every memory cell has a unique address, and the second characteristic is that it takes the same amount of time to access every cell. Well, with direct access storage devices, we eliminate the second requirement, the equal access part of it. So in a direct access storage device, every unit of information still has a unique address, but the time needed to access that information depends on its physical location and the current state of the device. So, I mean, the best examples of these would be the types of disks that we talked about before, so like hard drives, CDs, DVDs, and so forth. So a disk will store information in units which we call sectors, and each of which would contain an address and a data block containing a fixed number of bytes. So what we're saying here is that we have a sector that has an address. So each sector has an address, but it also has a section for the data itself. Now, a fixed number of these sectors are placed in the circle on the surface of a disk, which we call a track. And it's worth noting that the surface of a disk will contain several tracks. So just think about how a disk is laid out, and just if you have a circle around, that's one track, and you can have several circles on the surface of this disk. And there's also a single read-write head that can be moved in or out to be positioned over any track on the disk surface. So I mean, we'll show an illustration here in just a second here, but the idea with this is that the disk is going to rotate at high speed under this read-write head, and this allows us to read the information on the disk. Here's an illustration of how a disk looks and how it would operate. So we have this surface that has several tracks around it. Now here we just drew a couple lines to illustrate it, but there would usually be a lot more lines that get drawn around in a circle, but each of these lines would represent one track, and each of these tracks would have a sector in it. So maybe this track that we're pointing to, maybe for example, we might have a sector right here, maybe there's a sector right here, maybe another sector right here, and so forth. So we have all these different sectors that just keep going around in a circle. I won't draw the whole thing, but just imagine that these sectors lie on this entire track that goes in a circle. So the idea is that we're going to rotate this disc really fast, and then we have this read-write head right here that's going to move forward and back to read the different tracks. So once it picks a track, then it's going to read the sectors that are on this track. The access time to any individual sector of a disk is made up of three components, which we call the seek time, the latency, and the transfer time. The seek time is the time needed to position the read-write head over the correct track. The latency is the time for the beginning of the desired sector to rotate under the read-write head. And then the transfer time is the time for the entire sector to pass under the read-write head and have its contents read into or written from memory. Now, these values are going to depend on the specific sector that's being accessed and the current position of the read-write head. The second type of mass storage device uses the old access technique that we call sequential access. So a sequential access storage device, or SASD, does not require that all units of data be identifiable using a unique address. So to find any given data item, we must search through all the data sequentially. So we're just repeatedly asking ourselves, is this what we're looking for? And if not, we'll move on to the next unit of data and ask the question again. And eventually we'll find that we'll either find what we're looking for, or we'll come to the end of the data and conclude it's not there. But the whole point here is, instead of being able to look at random spots in our device or looking at a specific address, we have to search through the whole thing from beginning to end. So a good example of this would be tapes. And these would behave just like the old audio cassettes from back in the 80s and 90s. So if we wanted to find a specific song, you'd have to run the tape for a while and then stop and listen. Or you may be able to fast forward a little bit, then you'd stop it and try to see if you hear it. Or you may have to rewind a little bit. And we just keep repeating this until we actually find the song that we're looking for. So the same thing here is applied for tapes, where we're just trying to search the whole thing to find the piece of data that we're looking for. One of the fundamental characteristics of many I/O devices is that they are very, very slow when compared to the other components of a computer. So, like, for example, let's say we're trying to access something in our memory. The normal access time is about 10 nanoseconds, which is really fast. But the time to complete an I/O operation, so maybe locate and read a disk sector, will take about 10 milliseconds. Now, these types of units, like nanoseconds and milliseconds, they're very small compared with human timescales. It's sometimes difficult to really understand and appreciate the difference between these times. So, I mean, the whole point here is that this difference is 10 to the power 6 times slower, or a factor of a million, or 6 orders of magnitude, or however you want to interpret that. That's a huge difference. So let me put this in a different perspective just to kind of show you how big of a difference we're talking about between 10 nanoseconds and 10 milliseconds. Let's say that we're trying to like travel or something, maybe traveling so many miles. So this difference in the orders of magnitude would be like traveling a mile compared to 40 complete revolutions of the Earth's equator. Or even in terms of time, the difference we're talking about is between a day and 30 centuries. I mean, that's how big of a gap that we're talking about as far as the access time is concerned. So I mean, it's not uncommon for I/O operations to be this much slower. And because of these differences, it does make it kind of difficult to deal with I/O devices and main memory at the same time, because we have these different speeds. Now, there is a solution to this. We can use a device that's called an I/O controller. So an I/O controller is just simply a special purpose computer whose responsibility is to handle all the details of input-output and to compensate for any speed differences between the I/O devices and the other parts of the computer. It does have a small amount of memory, which is what we call an I/O buffer. And it has enough I/O control and logic processing capability to handle the mechanical functions of the I/O device, such as the read-write head, maybe the paper feed mechanism if we're talking about printers, and the screen display. It also is able to transmit to the processor a special hardware signal, which we call an interrupt signal, or just an interrupt. And this is usually done when an I/O operation is complete. So it just lets the system know that we're done with some type of I/O operation.